In this video, we will be doing two more examples from exercise 9.3 from the chapter of circles. So the first example that we'll do is question number 9 from this exercise 9.3, where we are given that two circles intersect at points B and C. So we have one circle and another circle. They intersect at points B and C. Through B, two line segments, that is ABD and PBQ, are drawn. So through the point B, we have a line segment ABD is drawn, and another line segment PBQ is drawn through the point B. So we have PBQ over here. So these are drawn to intersect the circles at the points A, D, P, and Q. So that means ABD is intersecting the circle at A and D, and similarly PBQ is intersecting the circles at points P and Q respectively. Okay, now we are asked to prove that the angles ACP and the angle QCD are equal. So what is the angle ACP? It is this angle here, subtended by between these blue lines here. So ACP is this angle over here. So let me mark that. So ACP is this angle over here, and the angle QCD is this angle over here, and we are asked to prove that these two angles are equal. Now the problem may seem to be difficult at first, but it is actually quite a simple problem and a very short problem. Okay, so it is appearing to be complex, but it is not complex. It is actually quite simple. Now, if we notice, the angle ACP is the angle subtended on the circle at the point C by the segment of the circle AP. So it is this segment over here, which I will highlight also in red, or let me use some other color. I'll use pink for that. So the segment AP of the circle, which is this segment over here, is subtending this angle ACP at the point C on the circle. But we also notice that the angle ABP is also subtended by the same segment of the circle. So ABP is an angle subtended by the same segment AP of this bigger circle. Similarly, what we notice is that the angle QCD is the angle subtended by the segment DQ of the circle. So it is this segment over here. It is subtending an angle QCD at the point C on the circle. But we see that the same segment DQ is also subtending an angle QBD at the point B on the circle. And we know from our theorems that the angles subtended by the same segment on the circle are equal. So that means the angle ACP and the angle ABP must be equal, because they are both angles subtended by the same segment of the circle. So with that information in hand, we can now write that angle ACP, so we have angle ACP is equal to angle ABP. And that is because both these are angles subtended by the same segment of the circle, and we know that angles subtended by the same segment of the circle are equal. So let's write that. So we can mark this as the angle ABP, which is this angle over here. So we have angle ACP equal to angle ABP because they are both angles subtended by the same segment AP of the circle. Similarly, if we look at the smaller circle here, the angle QCP is subtended by the segment DQ of the circle, and that same segment DQ is subtending an angle QBD at the point B on the circle. So we will now have angle QCD to be equal to the angle QBD, and these are equal for the same reason as we have written above. So I will not rewrite that, so I will just highlight it. It is equal because of the same reason. So these are also angles subtended by the same segment of the circle, and we know that angles subtended by the same segments of the circle are equal. So therefore we will have angle QBD to be equal to angle QCD. So we have these two relationships available with us now. So we'll call these two relationships as equation numbers 1 and 2. So we'll call the first one as equation number 1. So this is our equation number 1. Let me write that in a different color. So that's our equation number 1. And this is our equation number 2. Okay, that's the first information we have now. Now we also notice that the angle ABP and the angle QBD, these are vertically opposite angles. So these are formed by the intersection of these two lines AD and PQ. And we know that the vertically opposite angles when two lines are intersecting are equal. So the angle ABP is equal to the angle QBD. So we'll write that also. Angle ABP equals angle QBD. And why is that? That's because they are vertically opposite angles. And we know that the vertically opposite angles are equal. Okay, we have seen this from our chapter on lines and angles. Okay, now if we compare these equations, we have first shown that angle ACP equals angle ABP. Then we have shown that angle QCD is equal to angle QBD. And now we have shown that angle ABP and QBD are equal. So angle ABP, the right hand side of the first equation, and the right hand side of the second equation, which is QBD, so these are equal. So if the right hand sides of these two equations 1 and 2 are equal, that means the corresponding left hand sides must also be equal. So from equations 1 and 2, we can now write that angle ACP is equal to angle QCD. So the left hand side of equation 1 and the left hand side of equation 2 must be equal, because the right hand sides have been shown to be equal. So we have therefore proven that the angle ACP is equal to the angle QCD. So we can write now that from equations 1 and 2, from 1 and 2, we can show that angle ACP is equal to the angle QCD, and which is what we had to prove. We had to prove that the angle ACP, which is this angle over here, is equal to the angle QCD, which is this angle over here, and we have proved it in a very simple way. So the problem at first appears to be quite complex, but if you observe the construction and the diagram and apply the appropriate theorems, the solution is actually quite simple. Okay, so we've been able to solve it in a very small number of steps. So basically we have used the idea that the angles subtended by the same segment in a circle are equal. Okay, and then we have applied the property of vertically opposite angles being equal from our chapter from lines and angles. Okay, and from that we were able to prove that the angle ACP is equal to the angle QCD. Okay, now let us move on to the next question and solve one more problem from this exercise. So the next problem here that we have is question number 10 from the exercise 9.3, which is stating that if we have circles drawn taking two sides of the triangle as the diameter. So for example, we have a triangle ABC, and there are two circles drawn taking the sides of the triangle as the diameters. That means AB is a diameter of the smaller circle and AC is a diameter of this bigger circle. So the one side of the triangle is the diameter of a circle. The second side of the triangle is the diameter of another circle. And we are asked to prove that the point of intersection of these circles lie on the third line. So we are asked to prove that the point of intersection D here, this lies on the third line. So the third side of the triangle, which is BC, we have to show that the point of intersection of these circles, the point D, lies on the third side of the triangle. So the third side of the triangle is BC. Okay, so this again is quite a simple problem, given the fact that we have the lines AB and AC, the two sides of the triangle, as diameters of the circle. So to prove this, what we will first do is Let's first state the problem. We have to prove that, what is it that we have to prove? We have to prove that the point D lies on the third side. That means we have to prove that the points B, D and C lie on the same line, and that means we have to prove that B, D and C are collinear. Okay, so to prove points B, D and C are collinear, that means B, D and C are points on the same line, which we will also show that they are on the third side of the triangle, okay, which is quite visible. So to prove this, we will make a construction. So the construction is to join AD. So we will join the points A and D. So we join AD. So let's make a line AD, and I'll use a different color for that. So we are joining AD over here. So we have joined AD. Okay, now it's not appropriate. Let me draw it straight. So we have now joined AD. Now what we notice is that the angle ADB is an angle subtended by the semicircle because AB is the diameter of the circle. So the angle ADB is the angle subtended by the semicircle. So let's write that. Now angle ADB is an angle subtended by a semicircle or by the semicircle. Okay, and how do we know that? That is since AB is diameter. Okay, AB is diameter of the circle. So therefore we can say that the angle ADB equals 90 degrees. Why is that? We know from our theorem that the angle subtended by the semicircle is a right angle. So let's write that. So now that we have that the angle ADB is 90 degrees, so that means this angle here, angle ADB, is a right angle. Next, in a similar way, if we look at the angle ADC, which is this angle over here on the right side, ADC, this again is an angle subtended in the semicircle of this bigger circle because AC is the diameter of the bigger circle. So angle ADC, which is this angle here, that is also 90 degrees. So we can write also angle ADC equals 90 degrees. And why is that? That is because the angle ADC is also the angle subtended by the semicircle, and we know that the angle in a semicircle is 90 degrees, and therefore we will have this particular angle here, the angle ADC, as also 90 degrees. So now we have the angle ADB is 90 degrees and also the angle ADC as 90 degrees. So what is the angle BDC? So clearly the angles ADB and ADC are a linear pair of angles, and the sum of these linear pair of angles is 180 degrees. That means B, D and C are all on the same line. So we have now shown that the angle ADB plus the angle ADC is 180 degrees. So that means the points B, D and C are on the same line because the angle on that line is 180 degrees over here. Okay, so therefore we can state that angle BDC equals 180 degrees. So that means the points B, D, let me write that properly, the points B, D and C are collinear points. Okay, they are collinear, and they also are clearly lying on the third side of the triangle ABC. Okay, and we clearly see that D lies on the third side BC of the triangle. So D lies on the third side, which is BC of triangle ABC. Okay, so we were asked to prove that the point of intersection of the circles, or that is this point of intersection, lies on the third line or the third side of the triangle ABC, and we have shown now that D is collinear with B and C, so therefore D lies on the same line BC, and BC is also the third side of the triangle ABC. So therefore the point of intersection of the circles, the point D, lies on the third side of the triangle ABC, which is what we were asked to prove, and hence this has been proved.